All right, good afternoon, everyone. Thanks for your patience and thanks for joining. It looks like most of our attendees have joined at this point, so I think I'll go ahead and get started. Again, just a reminder, if you'll please keep your microphones muted during the presentation, and I will try to answer some questions towards the end of the meeting, which, if you don't mind, I'd prefer to have submitted through the chat feature within GoToMeeting. So if you send a chat with your questions at any point during the session, we can discuss those towards the end of the meeting or follow up afterwards. So my name is Dennis Masuda. I'm the engineering manager at Optimized Thermal Systems. And today we're just going to go through a brief demonstration of our CoilDesigner software. This is really just a basic overview of the capabilities of the software and a demonstration of some applications of how the tool can be used for any interested new users. You should be able to see my screen right now, which I'm sharing with the group. And I'm going to walk through just a demo of the application of the software. Before I begin, just as a bit of introduction, I want to just briefly describe Optimized Thermal Systems and CoilDesigner for those of you who aren't familiar. I suspect that most of our guests today have become familiar with OTS through our webinar series that we hosted with the International Copper Association over the last few months. And the purpose of this session is really to give a little bit more background on our CoilDesigner software. But by way of introduction, Optimized Thermal Systems is a consulting company that grows out of the research that's been conducted and continues to be conducted at the University of Maryland, College Park, and their Center for Environmental Energy Engineering. This department has developed some state-of-the-art tools for modeling heat exchangers and vapor compression systems. And out of that work, several commercial software packages have been developed, which OTS has the licensing agreement to distribute. So the tool I'm going to be showing today is called CoilDesigner, and this is a tool that OTS distributes commercially, uses for consulting work, and has licensing rights to customize for our customers as well. And the purpose of the tool is really for the simulation of heat exchangers, both tube and fin, microchannel, as well as some coaxial heat exchanger types and a few other variants that I'll show. So with that, I'll go ahead and get started with the demonstration. Up on my screen right now, you should be able to see the blank CoilDesigner window before I've started any work. And I'm going to go ahead and walk through the process of creating a model for a tube and fin heat exchanger. So I'll start by going to File and New, and this will start up a new coil wizard, which will walk me through the steps to configure a heat exchanger that I can then use for simulations. As I start walking through the steps of this process, the software will ask me which type of heat exchanger I'd like to model, and here you can see the capabilities within CoilDesigner. So for this example, I'll focus on a tube and fin heat exchanger, but we also have the ability to simulate a microchannel heat exchanger, coils with flat tubes, wire fin and tube heat exchanger, and so-called coaxial tube and tube heat exchanger. And after I go through this demonstration, if we have time, I can also demonstrate the microchannel interface as well. But one of the nice things about the software is that all of these heat exchanger types can be modeled through a very similar process through the same user interface. So the process that we show here for the tube and fin coil will be very much the same for the other coil types. So with this selected, I go into the basic setup of the solver and the model of this coil. First, I have to choose the type of solver, and the default here is the fast solver. This is typically recommended for most of our simulations, but we have some capabilities to implement more advanced solvers later on down the line as we fully configure our model. we can implement these additional solvers that may allow for non-uniform mass flow through the coil or conduction through the fins in the heat exchanger. So right now I'm going to go with this fast solver, which is appropriate for most applications to start. Now, the working principle behind CoilDesigner is that it is a finite control volume based model. So that means is we're looking at a heat exchanger and we're breaking it into a large number of different control volumes, and then within each of these control volumes we're calculating energy and mass balances that propagate through all of the segments of the heat exchanger. And so to specify our model, we need to state the number of segments that we'll be dividing this heat exchanger into for evaluation. And so we typically divide the heat exchanger up in terms of the number of segments per tube. So you may have a heat exchanger with a large number of tubes. We'll break each of those tubes into several segments and solve those equations out in each segment. Here I'll start with a default of 10 segments per tube, and typically we recommend having segments that are less than 10 centimeters each for good calculations. And this is something that you can experiment with on your own to understand the trade-offs between speed and accuracy of including more or less segments within your model. So now I'm going to really begin the process of outlining the geometry details of the heat exchanger that we are configuring here. And the first step in that process is defining the tubes of the heat exchanger. So here we can have a heat exchanger that has inline tubes, as shown in this diagram, or staggered tubes. And we can go through the process of specifying the number of tubes and their dimensions. So in this case, for this example, I'll just begin with a heat exchanger that has 24 tubes per bank, as we call it. This is in the transverse direction. If we were looking at the face of the coil, be the number of tubes going upwards. And then I'll specify 2 tube banks, and then this is the number of rows in the airflow direction. So here we have a 24 by 2 coil. The next thing I'm going to do is enter the dimensions of the tubes. Let's say that these are about 1/2 meter long, and I want to demonstrate some of the capabilities of the software for smaller diameter tube heat exchangers. So we will put in the details of a 5 millimeter tube coil. Now you can see here I'm entering my dimensions in millimeters, and that's because that's a setting that I've personally set on my system. But this is something that can be customized by each user so that the default values are in whatever units you prefer, and the conversions can take place automatically within the interface. So I'll go ahead and enter the dimensions between tubes, the horizontal and vertical spacing. And then we have the ability to enter the details of the tubes internally as well. So if we have smooth tubes, we check this box here. But if we have enhanced or microfin tubes, we can enter all of the geometry details that pertain to that tube type. So here I'll put in some dimensions for 5 millimeter microfin tube. And all of these characteristics are defined in the drawing that I just pulled up there, which you can access with this button. And with that, we have entered all of the information that's required for specifying the geometry of the tubes. And the next step is to move on to the fins. So in this case, I want to look at specifying the dimensions of the fins themselves, so the thickness of the fin and the fin density. And here we define that in terms of fins per inch, which I'll set as 15 fins per inch. And we have a number of options available to us for the type of fin. So we can have flat plate fins, we can have slit fins, louver fins, wavy fins, or even just bare tubes that don't have any fins on them. In this case, I'm going to pick a louver fin configuration. And you can see when I select a fin type, drawing pops up here on the right side that tells me the dimensions that I need to enter to define that fin. With this louver fin, I know that this horizontal louver pitch is about 1.6 millimeters, and the height of the louvers is about 1 millimeter, so I can enter those geometry details in here. The next thing I'm going to do is enter the refrigerant that's used in the heat exchanger. And I have a lot of options here. We support the refrigerants that are, majority of the refrigerants that are in the NIST RefProp database. So you can see this dropdown contains all of the working fluids that we typically encounter in the HVAC industry, as well as some other brines and water, some natural refrigerants and other fluids, and some proprietary fluids as well. So we can select our refrigerant. In this case, I just want to model R410A, so I can select that from the drop-down list. And our external fluid is air. And there's some more flexibility here if that's desired. If you have a proprietary fluid that we don't have yet in the software, you can add your own fluid properties directly into the software and load that in. Or if you're investigating mixtures, you would even be able to define a user-defined mixture by specifying different constituent components here of different refrigerants and a mass fraction for each of those. So with these selections made, I can move on to the final step of the initial setup of this coil, and this is to select the heat transfer and pressure drop correlations that are used in the calculation of the heat exchanger's performance. So this is really the foundation of how CoilDesigner works. The calculations that it performs are based on empirical correlations that come out of the literature from various peer-reviewed papers where authors have characterized the heat transfer and pressure drop performance of fins and tubes. So to specify the performance of this heat exchanger, it's important that I get accurate predictions of heat transfer and pressure drop for the surfaces that we're working with. So you saw before that I specified louver fins, and I therefore need to select a correlation on the air side that's appropriate for louver fins. So when we drop down our list, we can see the large number of correlations that are available for different fin types. And because we're talking about louver fins, we move on to these three options here that are given for louver fin heat exchangers. And one of these we know was recently developed at OTS specifically for small diameter tube fin heat exchangers. So we're building here a 5 millimeter coil. So we're going to select this correlation that is valid for the 3 to 5 millimeter tube diameter range. So if I select this correlation will be used to calculate heat transfer coefficients on the air side with these fins. And I'll do the same thing on the pressure drop side. I can use this author's correlation to predict the air side pressure drop for my small diameter louver fin heat exchanger. And I'll follow through the same process for the tubes. You saw that we specified microfin tubes for this coil, so we want to select correlations that are valid for microfin tubes as opposed to smooth tubes. And I need to specify heat transfer and pressure drop correlations for each phase of refrigerants, liquid, two-phase, or the vapor region. So for the liquid and vapor phase in a two-phase heat exchanger, these don't make an enormous contribution towards the overall performance, but we want to capture the performance nevertheless. And here I'm going to pick a correlation that is specified for microfin or internally enhanced tubes. So I can select that for my heat transfer coefficient for liquid phase, as well as vapor phase. And I'll do the same thing for pressure drop to specify a microfin correlation for the liquid phase and the vapor phase. And now finally, I need to specify the performance in the two-phase region. And at this point, we need to distinguish between whether or not we're modeling a condenser or an evaporator. For this particular model, we're going to focus on a condenser. And so from that, I need to select correlations that are valid for a condenser. You can see we have correlations for evaporators, correlations for condensers. Some of these are very specialized. They work specifically for CO2 or specifically for ammonia. In this case, we want to find a correlation that is applicable for our microfin tubes and for condensation. So we'll select this correlation from Koyama. And we'll do the same thing for the refrigerant pressure drop in two-phase. And with this, we've set up the fundamentals of this heat exchanger. We've carefully gone through to consider the heat transfer and pressure drop performance for both surfaces. And we now have the framework to perform simulations with this heat exchanger. I should also mention we have the flexibility to add your own correlations, to customize or tune those correlations based on lab data or CFD simulations. If the correlations that exist in the literature that are included aren't applicable for your particular heat exchanger type or aren't matching well with your lab data, there's always room for customization of the tool by each user. Now, after completing this walkthrough, I get the main screen showing me my newly configured heat exchanger. On the left side, I can see a grid that represents if we were in the airflow direction looking at the face of the coil. And the reason this is divided up into a grid is because we've specified in setting up this coil 10 segments along each tube, and we have 24 tubes vertically. And so this grid allows us to import airflow data. So if we have information from an experiment or from a CFD simulation, we can specify different velocities, temperatures, relative humidities at different locations entering the face of the coil. So it allows us to account for airflow maldistribution and non-uniformity. Considering the tube side, you can see we have arrows here on the left flowing from left to right, and our tubes are shown on the center of the screen as if they were going into the screen of the computer. Now, these tubes right now are just a blank canvas, and we can specify the circuitry however we like. Now, that means I can go right into this interface and directly click to define my circuitry by clicking between any two tubes. If I hold Shift, I get a connection on the opposite side. And I can set individual tubes as inlets or outlets in any pattern that I like. Now, for this example, I'm just working with a very simple counterflow circuitry. So I can use one of the features within Project, Generate Circuits, to automatically build this circuitry. So here I just want to have two counterflow circuits constructed for this heat exchanger. When I click OK, that will generate this counterflow configuration of circuitry where the flow comes in at tube 25, goes back and forth and down, and then crosses over at the middle of the heat exchanger and comes back up and exits at tube number 1, and the same with this second circuit down below. So now we've entered all of the geometry details of the heat exchanger, the circuitry. The next step is to define the flow conditions that the heat exchanger is going to be experiencing. So to do that, I can go to Project, Edit Air and Refrigerant Inlet State, and this is one place where I can very simply specify the overall air velocity and air flow conditions and the refrigerant flow conditions coming into the heat exchanger. Now, I mentioned this would be a condenser, so we want to specify a refrigerant state that makes sense for a condenser. The software is able to model a condenser, an evaporator, or a single-phase heat exchanger, but we need to specify operating conditions that thermodynamically make sense at that inlet. So for this condenser, we would specify a pressure and temperature. That is one convenient way to specify the superheated vapor state that would typically enter a condenser. And that means I can put in my pressure, temperature, and mass flow rate on the refrigerant inlet side. In this case, I can specify that would be about let's say 2.7 megapascals, and the refrigerant temperature is going to be about 322 Kelvin, which is 120 F. And then we can set the refrigerant flow rate, in this case about 28 grams per second. On the air side, we can set the pressure, the temperature, and the relative humidity. And then to specify the airflow rate, we can enter the airflow rate in terms of volumetric flow rate, here 1 meters cubed per second, or we can specify the velocity at the face of the coil. So I'll go ahead and enter these conditions, and this will define our tube and fin heat exchanger and allow us to run a simulation. So when the simulation is completed, these are what those results will look like. And this is a dashboard that shows us the summary of how our heat exchanger is performing. So on the left side, we have tabular outputs of all of the performance information for this coil. We have information about the heat load. This is a condenser, so it's all sensible heat. But we could look at the latent load or condensation if this were an evaporator. We have an estimate of the charge of refrigerant inside the heat exchanger, summary of the flow rates, pressure drops on the air and refrigerant side, as well as the outlet states for both fluids, and some summary information about the heat transfer area, heat transfer coefficients that were calculated in the model, as well as overall summary information about dimensions, mass, and we can put in our own functions for cost if that's an objective for this exercise. On the right side, you can see a summary of some of the performance shown graphically. We can see the comparison between sensible and latent load. We can see the visualization of the heat transfer coefficients of the different surfaces, where we can see the refrigerant side heat transfer coefficients are obviously much larger than the air side heat transfer coefficient. And then we can see the distribution of the phases of refrigerant inside of this heat exchanger. And on a length basis, we can see that a small amount of the heat exchanger is occupied by superheated vapor. About half of it is occupied by two-phase refrigerant, and then about half of it is occupied by subcooled liquid. So, the state point we've specified here, we can see is probably not as much mass flow as this heat exchanger could handle. We have a very large subcooled region, and we could get more capacity out of it if we ran with a higher mass flow rate. So these kind of tools are useful for making those kind of assessments to understand what's happening in our model when we run a simulation. And we can see these results in tabular form, and we could look down even into very low-level details to see, for example, the temperatures or vapor quality at every segment of every tube. And this allows us to do things like identify the location where phase change occurs. Here we can see, for example, in tube number 24, there's a change of phase occurring. And we can explore exactly how the inner workings of our heat exchanger look. There's additional plotting functionality here for understanding the distribution of heat load against tubes or temperatures along the coil face. And we can see a visualization of the temperatures on our heat exchanger. And we can export all of these results to Excel or as a PDF for storing that information. So this is already a fairly powerful tool for just simulating one given heat exchanger, but we can continue this process and really use this as a tool to aid in heat exchanger design. So one of the functions I want to show here is the parametric analysis capability. So if I go to Project and Parametric Analysis, here I can define a parametric study where I can vary geometry parameters of the heat exchanger or flow conditions entering the heat exchanger and study the impacts that these different parameter changes have on the model's performance. So the parametric analysis is up on my screen here now. And within here, you can see various geometry parameters within the heat exchanger that we could alter. We could apply different correction factors to our different correlation predictions. And we could vary things like the air side inlet conditions or the refrigerant stream conditions coming into the coil. So just as an example, I could look at what happens when I change my fin density from 15 fins per inch up to 20 fins per inch, for example. And if I do something like this, I can update my parametric table. I can simulate my, my coil under these different conditions, and I can quickly assess the impact of the performance change that occurs when I add greater fin density. Here you can see I have an increase in heat load and an increase in pressure drop as I get more fins, as we would expect. But we can also extend this to multiplicative studies where we look at different parameters in combination. So if I also want to study changing the tube length or the airflow conditions, I can very quickly evaluate a large number of different designs within this interface. And so there are some options here where we can look at individual pairings of changing these values. Here we change the tube length across the full range while keeping the fin per inch the same. And then we change the fin per inch while keeping the tube length the same. We can do a combination where we change both parameters at the same time. Or probably the more useful of these options is the multiplicative study, which gives us every pairing of all of these different combinations of parameters. And we can easily think of thousands or tens of thousands of different combinations that we might want to evaluate for a heat exchanger. And here you can see we can very rapidly evaluate all these different combinations of heat exchanger designs, and we can extend that even further. You also may have noticed that on this simulation, two results were showing up simultaneously, and that's because we're running these simulations in parallel. Here I've specified that I want to run 2 runs in parallel, but if you could run this simulation on a workstation or a server with a larger number of processors, you could conceivably run on a large number of cores and very quickly evaluate thousands of designs right within this tool. So with that, we have a coil model built. We have an assessment of its performance and some studies of the effect of changing various parameters. We also have the ability to save this file when we go to save or save as. We create a file called CoilDesigner Heat Exchanger file. The extension is .chx, and we can load that back into CoilDesigner at any time. And we can run the same evaluations, same types of simulations, and make modifications to it at a later date. But we can also read that into our other software, VapePsych, which allows us to plug in that heat exchanger into an entire vapor compression cycle model. And this would allow us to simulate the impacts of multiple heat exchangers and compressor design changes to evaluate a full heat pump or air conditioner or refrigeration cycle while maintaining all of the modeling detail of one of these very detailed heat exchanger simulations. So that is one of the other extensions of this tool is the ability to not just evaluate the heat exchanger performance, but also the entire cycle's performance. So very quickly, I want to just demonstrate a microchannel heat exchanger as well, and walk through some of the steps for configuring that, just to demonstrate the concept very briefly. All right, so here again you can see another blank CoilDesigner file or interface, and here we can start a new coil file again. But this time we want to make a microchannel heat exchanger, and we have the ability to do a microchannel coil that has headers, or one that is a serpentine configuration, where it's a continuous microchannel tube that's bent between the different tubes vertically. Here I'm going to look at a microchannel that has headers. And again, we can set the solver information and the number of segments. And we can go ahead and enter this information about the tubes. So you can see the interface is very much the same. We have a tube configuration, and then fin, and then refrigerant. The same process is followed. For this particular design, I want to look at something with, let's say, a 12 millimeter vertical spacing between tubes. And the tubes here are 20 millimeters wide and 2 millimeters tall. Let's just say they have 1 millimeter ports with 15 ports per tube. And you can see that we can specify rectangular ports, but we can also put in circular ports, or we can enter additional information about the hydraulic diameter. If we have some non-rectangular or non-circular geometry, we can account for the performance of that by entering the hydraulic diameter and cross-sectional area of a port. The next step is to enter the information about the fins again, and here I can set my fin thickness and fin density. And with the microchannel heat exchanger, we typically see louver fins applied, and we can enter the geometry information for the louver fins in very much the same way as we can with the tube fin interface. So I'll just go ahead and leave these default values for now for the geometry of the fins. For the refrigerant, again, we have the same flexibility of different refrigerants. Here we'll just select R134A. And then finally, I'll go through this process of selecting appropriate correlations, where we'll select a correlation on the air side that is suitable for louver fins. We'll select correlations for liquid phase and vapor phase refrigerant that you would see in any heat transfer or fluids textbook for the single phase heat transfer and correlation and pressure drop correlations I've selected. And then in this case, let's make this an evaporator. So I'll select a correlation that is appropriate for an evaporator. Here, the correlation from Shaw for the heat transfer coefficient, and more recent correlation for pressure drop in an evaporator. So just like that, we've configured our microchannel evaporator, and you can see the interface is very similar to the tube and fin interface. But here in the center of our screen, we have our microchannel tubes, which are going into the screen, and the individual ports that are inside of each of these tubes. So we have the ability to specify really any header configuration we could imagine here. So we could have multiple passes of the heat exchanger, and we can do that by adding individual headers in a similar manner to how we add inlet and outlet states for the tube fin coil. But we also have another process to speed up the configuration of these. If we go to project and define microchannel passes, here we can specify multiple passes of the coil by the number of tubes, and it will automatically generate the headers for us. In this case, I'll just look at a single pass configuration for simplicity. When I say OK, that'll generate my header configuration. And here you can see in the front of the screen here in red, that's my inlet header, and the back of the screen in blue, that's the outlet header. And then to try this one out, we can enter the air and refrigerant inlet state again. And again, this is the same interface as we see in tube and fin. But since we're working with an evaporator in this case and not a condenser, we need to specify an inlet condition that makes sense for an evaporator. So in an evaporator, we typically have two-phase refrigerant entering. And so I can specify here saturation temperature, or an evaporation temperature as it might be called. And the vapor quality, the percent vapor quality at the inlet to the evaporator. And then I can set the refrigerant mass flow rate, and the same conditions with the same conditions apply with the inlet air. Let's say that we're going to operate with 27 degrees C air with a 7 degrees C evaporating temperature. And with this information, I should be able to simulate this coil and get a prediction of its performance. And here's a look at my overall heat exchanger performance. You can see, again, very essentially identical display to the tube and fin interface. So with that, I think I have covered the main features I'd like to include in this demonstration for both the tube and fin and the microchannel interface within CoilDesigner. And I'll go ahead and give a couple of minutes if anyone wants to submit additional questions through the chat feature. I can review those and provide some feedback. I'll go ahead and start reading through those at this time. So we received a couple of questions. I'll start from the top. We have one question coming in about how to model tubes if they have different lengths. Maybe one row has a different length than the second row. This is something we would definitely encounter in something like a condenser coil, an outdoor unit that has a bend, a U-bend, or an L-shaped bend. At this point, we don't have a way to do that within the interface of the software, and typically we just use the average length of the two tubes. And in general, this gives us predictions that are reasonably close to what we see in the experiment. There is a question about having multiple subcooling lines, or and I think that this is really answered by the customization of the circuitry. I showed a very simple circuitry here for this tube fin coil, but conceivably we could have any number of circuits defined here. They could have different lengths, and we can account for the performance of each of those individual circuits based on how we've defined them in the model. We also have the ability to enter feeder tubes upstream of the coil. So for each inlet coming into the heat exchanger, we can specify a diameter and length of the tubes that feed it. And there's another question asking if rows have different numbers of tubes, how can that be modeled? One option for doing that is to use plugged tubes. So for example, if I have in this model that I've shown previously, where we have 24 tubes vertically, if one of these tubes is, if one of these rows does not have the same number of tubes, say the second row has less tubes than the first row, I can make some of these tubes plugged. So for example, I can make this tube essentially disappear and it won't be simulated, and I can continue to do that to have a different number of tubes. And that's about the level of flexibility that's available within the interface. If you want to have less tubes or more tubes in different rows, you can block them off so that they're not simulated. There's another question about leaving, again, kind of leaving out a notch for some interference that's blocking flow, and we can account for that by specifying the air velocity profile that comes into the heat exchanger. So if we have, the assumption here is that everything is uniform, which is rarely the case. But if we want to specify that some particular section of the coil doesn't receive airflow in the same way that the rest of the coil does, we can reduce or eliminate reduce the velocity of the air that enters a particular segment. So if you think of this as a grid, we can specify any part of this this coil face area and reduce the velocity there to represent something more realistic as far as what is the real velocity distribution when you have all the blockages and non-uniformities that come from the enclosure where this coil is actually installed. And so one place where we can do that is within Project Edit Airside Parameters. And this is an interface that lets us specify temperature, relative humidity, and velocity across this entire grid. Of course, we're not going to do that by hand, but we have the ability to load and save files of this type. So if you have data on your airflow distribution, or you want to create something, some template in Excel, or you have data from CFD simulation, we can go through here and load in an airflow profile that blocks off part of the coil, or maybe it has a gradient where the top of the coil sees a different velocity than the bottom of the coil, if we're talking about some type of enclosure or a coil configuration, for example. So we have some flexibility there for how the airflow configuration is specified. So I see one feedback saying someone's getting an error when trying to follow my model. I guess there must be some difference in the values that you entered, and we're happy to answer those questions through our support email address, which I'll just go ahead and put up on the screen. And this is one of the features that is provided to our CoilDesigner customers is technical support by our engineers at OTS. We can receive your heat exchanger files, review them, and provide some guidance as to where things may be going wrong. In this case, I think any number of entries in terms of geometry or correlations that don't match for the particular heat exchanger that we're looking at could always yield errors, and our staff is available to help provide that guidance in terms of fixing models that aren't working. There's a question about liquid overfeed coil simulation. This is one I think I can take offline. If you want to follow up with me by email, we can discuss that particular application further. And there's a question about tube orientation. If the tubes are not horizontally oriented, it's a good question. So in general, we see that the gravity effects in most tube fin and heat exchangers of the size range we see in HVAC, usually these effects are not extremely influential over the overall performance, and we can get reasonable results whether or not the tubes are oriented vertically or horizontally. But fundamentally, the question comes down to how the correlations were developed. So CoilDesigner is really just based on these empirical models that authors have published for heat transfer and pressure drop performance in tubes. And so the majority of these authors developed those correlations for tubes in a horizontal configuration, but there's certainly literature out there that provides performance information for tubes that are vertically oriented. And so that's something that can be customized by an individual user. You can add correction factors or add your own correlations if you find that these kind of gravity effects from having vertical tubes are very significant. And there's another great question about the selection of correlations. I think it's one of the most overwhelming features looking at the software. There's a very large number of of correlations that are available to the user, and it's often desirable to have some guidance for the selection of those. Right now, we don't have any summary document that really that provides guidance on a general selection for all options, but we do offer, as part of the licensing, technical support and training. So each new user is entitled to training with the OTS team. And typically in those training sessions, we go through something like this demo process that we just saw today, but we do it in a customized manner. So we'll look at a particular coil that is of interest to your company, and we'll go through all the steps to model that, validate that model, and in that process kind of provide some guidance as to what type of correlation is appropriate for your application. And we try to train you through that process so that you can internally develop some experience with the right selection correlations for your particular application, because it can certainly vary significantly from different fields and different product lines and manufacturers. But it is something that we are working towards providing some more general guidance in terms of the best correlations, but often really making the best selections comes down to having experience with the tool and understanding of experimental performance from your particular product. All right, so I'll hang on a couple of minutes in case any more questions come in, but we'll be available to kind of work with you if you run into any issues. If you want to contact us at our support email address. I believe that all of our invitees to this session should have access to the software on a temporary trial basis. If you need help with configuring that, you can reach out to us at the same email address. And then for any other additional kind of sales questions about the software, the trial license, you can contact Tom Dresch. I'll leave these up for a couple minutes and wait if anyone has additional questions, but otherwise I'll thank you all for your time, and we'll be in touch if we can provide any additional assistance with evaluating CoilDesigner. So I hadn't initially planned to offer that up. There's a question coming in about watching this video again after this session is over. I have recorded the session, so I can look into whether or not we can host that on our YouTube page or something. Beyond that, we also have another demonstration from our third webinar for the ICA educational series. And part of that webinar includes a demonstration of tube fin coil in CoilDesigner, and that is also up. So we'll try to follow up with everyone to provide some additional materials for review after the session's over. All right, everyone. It looks like that's the extent of the questions that are coming in. Again, you can contact us by email, and I appreciate everyone's time for joining, and look forward to hearing from you in the future. Thanks again. Bye.